Hello everyone, my name is Fahmid Morshed Fahid. I am a third year PhD student in computer science at North Carolina State University. I work at Center of Educational Informatics under Dr. James Lester. Today I'll be presenting our work on progression trajectory based student modeling for Novice block-based programming. Block-based programming environments are simple programming tools, often designed so that students can drag and drop blocks to create logic. The environments have visual blocks with colors and shapes to guide the users. As such, block-based programming environments are often used in introductory CS courses. Studies show that these environments reduce cognitive load and increase engagement among learners. Other studies found that block-based programming environments can reduce coding errors in programming activities. But these environments are not perfect and still needs much improvement. One way to achieve that is to leverage student modeling. Student modeling is an approach that models students' interactions using a learning environment to analyze, evaluate, or to predict their learning behaviors. Trying to model students using block-based programming environments are difficult. Firstly, because programming activities in these environments are often open-ended. They have many solutions and multiple paths to follow. Secondly, the structure of problem solving in programming activity is iterative. Student goes from planning phase to coding phase to testing and revising phase. As such, intermediate steps are important. To summarize, modeling students using their final code is not sufficient. In our work, we have used progression trajectory-based student modeling that uses students' intermediate codes to model their progression towards a solution. Progression trajectory-based student modeling is a time series representation of students' block-based programs. For this, we incrementally analyzed students' progress towards a solution in a programming activity by looking into their programming code at different times and comparing them with corresponding expert author solutions. Prior work have used student modeling to understand generic learning behavior in block-based programming environments. For example, Wiggins et al. Used student modeling to understand how and when students seek for help. In another study, Toriano found 4 distinct clusters of students when considering how their programming concepts evolve over time. More recently, Jiang et al. Analyzed students' programming activities and found 4 different types of novice learners in block-based programming environments. These were quitters, approachers, knowers, and solvers. Similar type of student behaviors were also observed in non-block-based programming environments. Note that these studies are focused on finding generic patterns among students. In our work, we are investigating generic patterns of students' programming activity progressions. In other words, we asked, are there common patterns of progressions in individual programming activities, and if so, are they meaningful and can we predict them? For our study, we have used Prime, a block-based programming environment built on top of Google's Blockly framework. The learning environment contains 20 programming activities divided into 3 units and are designed to support non-CS majors in their introduction to CS courses. The programming activities are organized incrementally, meaning skills learned from the previous programming activities are applied in the later ones. We collected our data from an introductory CS course taught in a public university in the United States. The students received extra credit for completing the programming activities. For our study, we have used 5 programming activities from Unit 1. A total of 149 students attempted all 5 programming activities along with a pre-test and a post-test assessment. More details about the study can be found in the paper. The data was collected from student interaction logs with the Prime learning environment. The interaction contained 16 system-level user actions and workspace snapshots of their programming codes at different moments. The workspace snapshots were taken after every 30 seconds and were saved as XML strings. In total, there were 745 student activity pairs, each containing on average 20 workspace snapshots. Now let us understand how we modeled our progression trajectories. We converted a workspace snapshot at time t to the corresponding Python code. Then we used AST to remove comments, whitespace, and to normalize variable names. We repeated the same process using an expert solution for that particular programming activity. After that, we calculated the Demerio-Levestein distance between the workspace at time t and the expert solution. The distance is then converted to a percentage to calculate the similarity. By plotting consecutive similarities at time t, t+1, and so on, we created a time series representation of our students' progression towards a solution. In other words, a progression trajectory. We have used one expert solution for each of the 5 programming activities. These solutions were of minimum length with best block-based programming practices. To understand generic behavior in individual programming activities, we asked, are there distinct patterns in students' block-based progression trajectories? To answer our first research question, we clustered the progression trajectories using k-means clustering. We have used dynamic time warping as our distance metric and distortion elbow for selecting the number of clusters. We have found 3 distinct clusters, namely early quitting or the EQ cluster, high persistence or the HP cluster, and efficient completion or the EC cluster. Here are 10 randomly sampled examples from each of the cluster. As we can see, progression trajectories in the early quitting cluster did not spend much time nor did make significant progress towards the solution. Progression trajectories in high persistence or the HP cluster are very persistent, spends significantly more time in each of the programming activity while rapidly changing the similarity. Finally, progression trajectories in the efficient completion or the EC cluster are efficient in their progress, spends a little more than 5 minutes to complete or are close to completing the programming activities. For our second research question, we asked, are these patterns associated with meaningful differences in their programming behavior and learning outcomes? To understand that, we analyzed these clusters based on different characteristics. First, we looked into the completion rate in each of the 3 clusters. See that about 81% progression trajectories in early quitting cluster never finished their programming activities. In the high persistence cluster, there are almost equal number of completed programming activities and incompleted programming activities. Finally, in the EC cluster, 79% of the progression trajectories successfully completed their programming activities. In short, any progression trajectories that belong to the EQ cluster is more likely to leave the activity unfinished, whereas any progression trajectories in the EC cluster is more likely to finish the programming activity. For HP cluster, it is uncertain. Next, we looked into the distribution of hint requests and restarts across the 3 clusters. As we can see, progression trajectories in the high persistence cluster requested significantly more hints and did more restarts than others. Also note that there is no significant difference between the other 2 clusters in both cases. For other interesting characteristics, please see our original paper. For our third and final research question, we asked, are these patterns predictive of students' future programming behavior? Here, we try to predict whether a student will change their progression cluster in the next programming activity or not. We used the interaction data of individual students up until the end of the current programming activity and trained a classifier to predict the behavior in the next programming activity. We used 30 features, 16 of them are from event logs, 9 of them are relating to prior performance, and the rest corresponds to the current programming activity. For our experiment, we have used 4 classifiers, namely decision tree, random forest, logistic regression, and support vector classifier. For baseline, we have used 2. The base brief is a baseline that carries the current result forward, whereas the base measure predicts the majority class in the training set. The table shows the result of our classification task. As we can see, all classifiers outperformed both of the baselines. When compared against the base baseline, all the classifiers improved at least 9 to 14% higher when trained on all transitions. Also note that support vector classifiers outperformed all the other classifiers in all cases. To summarize our findings, first note that progression trajectories in efficient completion or the EC cluster typically do not ask for hint nor do restarts, but still makes quick progress towards the solution, often resulting in successfully completing. Whereas progression trajectories in the high persistence or the HP cluster spend significantly more time, ask multiple hints, and do multiple restarts to solve the problem, yet the final outcome is uncertain. Finally, progression trajectories in the early quitting or the EQ cluster quits early without spending much time and often leaves the programming activity unfinished. Also, they typically do not ask for hints or try restarting. In conclusion, we found that student modeling in block-based programming environment is challenging due to their open-ended structures. To solve that, we introduced progression trajectory-based student modeling. Our study shows that there are 3 distinct clusters with varying characteristics in these progression trajectories. We also showed that we can early predict whether a student is going to change their progression pattern in their next programming activity or not. There are a couple of future works to consider. First, a vector-based embedding such as code2vec could be used for embedding the workspace snapshots and better distance measure. Another direction is to add multiple solutions per programming activity, covering a wide range of possible solutions. In future, we might also run an empirical study with timely motivation to reduce early quitting and provide adaptive hints to encourage efficient completion and compare and evaluate our findings. I would like to acknowledge my co-authors, my colleagues, NC State and University of Florida, as well as the National Science Foundation for the support on the project. I would also like to thank UMAP for giving us the opportunity to present our work. If you have any questions or concerns, please feel free to contact me or ask me now. Thank you.